Hey, morning everyone. Welcome back. So last week you heard about logistic regression and generalized linear models. And it turns out all of the learning algorithms we've been learning about so far are called discriminative learning algorithms, which is one big bucket of learning algorithms. And today, what I'd like to do is share with you how generative learning algorithms work. In particular, you learn about Gaussian discriminant analysis, so by the end of the day, you know how to implement this. And it turns out that compared to, say, logistic regression for classification, GDA is actually a simpler and maybe more computationally efficient algorithm to implement in some cases. So, and it sometimes works better if you have very small data sets, sometimes, with some caveats. And we'll talk about comparison between generative learning algorithms, which is a new class of algorithms you hear about today, versus discriminative learning algorithms. And then we'll talk about naive Bayes and how you could use that to build a span filter, for example. Okay? So we'll use binary classification as the motivating example for today. And if you have a data set that looks like this with two classes, then what a discriminative learning algorithm like logistic regression would do is use gradient descent to search for a line that separates the positive and negative examples, right? So if you randomly initialize parameters, maybe it starts with some decision boundary like that, and over the course of gradient descent, you know, the line migrates or evolves until you get maybe a line like that separates the positive and negative examples. And logistic regression is really searching for a line, searching for a decision boundary that separates the positive and negative examples. And so if this was the malignant tumors and the benign tumors example, right, that's what logistic regression would do. Now, there's a different class of algorithm which isn't searching for this separation, which isn't trying to maximize the likelihood that the way you saw last week, which is, here's an alternative. It's just called a generative learning algorithm, which is rather than looking at two classes and trying to find the separation, instead the algorithm is going to look at the classes one at a time. First, we'll look at all of the malignant tumors, right, in the cancer example, and try to build a model for what malignant tumors looks like. So you might say, oh, it looks like all the malignant tumors roughly live in that ellipse. And then you look at all the benign tumors in isolation and say, oh, it looks like all the benign tumors roughly live in that ellipse. And then at classification time, if there's a new, patient in your office with those features, it would then look at this new patient and compare it to the malignant tumor model, compare it to the benign tumor model, and then say, in this case, oh, it looks like this one looks a lot more like the benign tumors I had previously seen, so I'm going to classify that as a benign tumor. Okay? So rather than looking at both classes simultaneously and searching for a way to separate them, a generative learning algorithm instead builds a model of what each of the classes looks like, kind of almost in isolation, with some details we'll learn about later. And then at test time, it evaluates a new example against the benign model, evaluates against the malignant model, and tries to see which of the two models it matches more closely against. So let's formalize this. A discriminative learning algorithm learns P of y given x, right? Or it learns right, some mapping from x to y directly. Or it can learn, I think Anand briefly talked about the perceptron algorithm. We'll talk about support vector machines later. It learns a function mapping from x to the labels directly. So that's a discriminative learning algorithm where you're trying to discriminate between positive and negative classes. In contrast, a generative learning algorithm it learns P of x given y. So this says what are the features like given the class, right? So instead of P of y given x, we're going to learn P of x given y. So in other words, given that the tumor is malignant, what are the features likely going to be like? Or given the tumor is benign, what are the features x going to be like? Okay, and then it'll also generative learning algorithm will also learn P of y. So this is also called the class prior. Excuse me, this probability, I guess. Right, it's called the class prior. It's just when a patient walks into your office, before you've even examined them, before you've even seen them, what are the odds that their tumor is malignant versus benign, right? Before you see any features, okay? And so, using Bayes' rule, if you can build a model for P of x given y and for P of y, if you can calculate numbers for both of these quantities, then using Bayes' rule, when you have a new test example with features x, you can then calculate the chance of y being equal to 1 as this. Right? Where P of x by the and so if you learn this term, P of x given y, then you can plug that in here. Right. And if you've also learned this term, P of y, you can plug that in here. Right. And P of x in the denominator goes in the denominator. Okay, so if you learned both of those terms in the red square and in the orange square, you could plug it into all of those terms and therefore use Bayes' rule to calculate P of y equals 1 given x. So given a new patient with features x, you could use this formula to calculate what's the chance that the tumor is malignant if you've estimated these two quantities in the red and in the orange circles. Okay, so that's the framework we'll use to build generative learning algorithms. And in fact, today you see two examples of generative learning algorithms. One for continuous value features, which is used for things like the tumor classification, and one for discrete features, which you can use for building like an email spam filter, right? Or I don't know, or if you want to download Twitter things and see how positive or negative the sentiment on Twitter is or something, right? So we'll have a natural language processing example later. So let's talk about Gaussian discriminant analysis. Right, GDA. Let's develop this model assuming that the features x are continuous values. And when we develop generative learning algorithms, I'm going to use x in Rn. So, I'm going to drop the x0 equals 1 convention. Right? So we're not going to need that extra x equals 1. So x is now Rn rather than Rn plus 1. And the key assumption in Gaussian discriminant analysis is we're going to assume that P of x given y is distributed Gaussian, right? In other words, condition on the tumor as being malignant, the distribution of the features is Gaussian. The feature is like the size of the tumor, the cell adhesion, whatever features you use to measure a tumor. And condition on it being benign, the distribution is also Gaussian. So actually, how many of you are familiar with a multivariate Gaussian? Raise your hand if you are. Like half of you? 1/3? No, 2/5? Okay, cool. All right. Oh, how many of you are familiar with a univariate, like a single dimensional Gaussian? Okay, cool. Almost everyone. All right, cool. So let me just go through what is a multivariate Gaussian distribution. So the Gaussian is this familiar bell-shaped curve. A multivariate Gaussian is the generalization of this familiar bell-shaped curve over a one-dimensional random variable to multiple random variables at the same time, to vector value random variables rather than univariate random variable. So if Z is distributed Gaussian with some mean vector mu and some covariance matrix sigma. So if Z is in Rn, then mu would be Rn as well, and sigma, the covariance matrix, would be n by n. So if Z is two-dimensional, mu is two-dimensional, and sigma is two-dimensional. And the expected value of Z is equal to the mean, and the covariance of Z. Well, if you're familiar with multivariate covariances, this is the formula, right? And this simplifies. We show in the lecture notes. You can get this from lecture notes. Sorry, and following sometimes semi-standard convention, I'm sometimes going to omit the square bracket. So instead of writing the expected value of Z, meaning the mean of Z, sometimes I just write it as EZ, right, and omit the square brackets to simplify the notation a bit, okay? And the derivation from this step to this step is given in the lecture notes. And so, well, the probability density function for Gaussian looks like this. And this is one of those formulas that, I don't know, when you're implementing these algorithms, you use it over and over. But what I've seen for a lot of people is almost no one, well, very few people start their machine learning and memorize this formula, just look it up every time you need it. I've used it so many times, I seem to have it seared in my brain by now, but most people don't. But when you use it enough, you end up memorizing it. But let me show you some pictures of what this looks like, since I think that would, that might be more useful. So the multivariate Gaussian density has two parameters, mu and sigma, that control the mean and the variance of this density, okay? So this is a picture of the Gaussian density. This is a two-dimensional Gaussian bump. And for now, I've set the mean parameter to 0. So mu is the two-dimensional parameter. This is a 0, 0, which is why this Gaussian bump is centered at 0. And the covariance matrix sigma is the identity matrix. So you know, well, so you have this standard. This is also called the standard Gaussian distribution, which means mean 0 and covariance equals to the identity. Now I'm going to take the covariance matrix and shrink it, right? So take the covariance matrix and multiply it by a number less than 1. That should shrink the variance, reduce the variability in distributions. If I do that, the density, the probability density function becomes taller. This is a probability density function, so it always integrates to 1, right? The area under the curve, you know, is 1. And so by reducing the covariance from the identity to 0.6 times the identity, it reduces the spread of the Gaussian density. But it also makes it taller as a result because, you know, the area under the curve must integrate to 1. Now let's make it fatter. Let's make the covariance 2 times the identity. Then you end up with a wider distribution where the values of, I guess the axes here, this would be the Z1 and the Z2 axes, the 2 dimensions of the Gaussian density, right, increases the variance of the density. So let's go back to the standard Gaussian, covariance equal 1, 1. Now let's try fiddling around with the off-diagonal entries. So right now, the off-diagonal entries are 0, right? So in this Gaussian density, the off-diagonal elements are 0, 0. Let's increase that to 0.5 and see what happens. So if you do that, then the Gaussian density, hope you can see the change, right? It goes from this round shape to this slightly narrower thing. Let's increase it further to 0.8, 0.8. Then the density ends up looking like that, where now it's more likely that Z1 and Z2 are positively correlated. Okay, so let's go through all of these plots, but now looking at contours of these Gaussian densities instead of these 3D bumps. So this is the contours of the Gaussian density when the covariance matrix is the identity matrix. And apologize, the aspect ratio. These are supposed to be perfectly round circles, but the aspect ratio makes this look a little bit fatter, but this is supposed to be perfectly round circles. And so when the covariance matrix is the identity matrix, Z1 and Z2 are uncorrelated, and the contours of the Gaussian bump of the Gaussian density look like round circles. And if you increase the off diagonal, then it looks like that. If you increase it further to 0.8, 0.8, it looks like that. Okay, where now most of the probability density function places value on Z1 and Z2 being positively correlated. Okay. Next, let's look at what happens if we set the off-diagonal elements to negative values, right? So actually, what do you think will happen? Let's set the off-diagonals to negative 0.5, 0.5. Right. Oh, wow. People making that hand gesture. Okay, cool. Right, great. Right. So you endow the two random variables with negative correlation. So you end up with this type of probability density function, right? And in contours, it looks like this, okay? Where it's now slanted the other way. So now Z1 and Z2 have a negative correlation, and that's 0.8, 0.8, okay? All right, so far we've been keeping the mean vector as 0 and just varying the covariance matrix. Oh, good, yeah. Yes, every covariance matrix is symmetric, yeah.
Should we be thinking of the sigma matrix as like a series of column vectors that point in some interesting direction based on those contour plots?
Should we think of the covariance matrix as interesting column vectors that point in interesting directions? Not really. Let me think. Maybe we should, yeah. No, I think the covariance matrix is always symmetric, and so I would usually not look at single columns of the covariance matrix in isolation. When we talk about principal components analysis, talk about the eigenvectors of the covariance matrix, which are the principal directions in which it points. But yeah, we'll get to that later.
The eigenvectors that would point in like the minimum and maximum gradients of the contour plots would be.
Yeah, so the eigenvectors of the covariance matrix point in the principal axes of the ellipse that's defined by the contours, yeah. Okay, so this is a standard Gaussian with mean 0. So the Gaussian bump is centered at 0, 0 because mu is 0, 0. Let's move mu around. So I'm going to move mu to 0, 1.5. So that moves the Gaussian, the position of the Gaussian density. Right now, let's move it to a different location. Move it to minus 1.5, minus 1. And so by varying the value of mu, you could also shift the center of the Gaussian density around. Okay, so hope this gives you a sense of, as you vary the parameters, the mean and the covariance matrix of the 2D Gaussian density, the source of probability density functions you can get as a result of changing mu and sigma. Okay, any other questions about this? I'll raise the screen. All right, cool. So, here is the GDA model. Let's see. So remember, for GDA, we need to model P of x given y, right, instead of P of y given x. So I'm going to write this separately in two separate equations. P of x given y equals 0. So what's the chance, what's the probability density of the features if it's a benign tumor? I'm going to assume it's Gaussian. So I'm just going to write out the formula for Gaussian. And then similarly, I'm going to assume that if is a malignant tumor, so if y is equal to 1, that the density of the features is also Gaussian. Okay. And I want to point out a couple things. So the parameters of the GDA model are mu0, mu1, and sigma. And for reasons we'll go into in a little bit, we use the same sigma for both classes, but we'll use different means, 0 and 1. Okay? And we can come back to this later. If you want, you could use separate parameters, sigma 0 and sigma 1, but that's not usually done. So we're going to assume that the two Gaussians for the positive and negative classes have the same covariance matrix, but that they have different means. You don't have to make this assumption, but this is the way it's most commonly done. And we can talk about the reason why we tend to do that in a second. Okay. So this is a model for P of y given x. The other thing we need to do is model P of y. So y is just a Bernoulli random variable, right? It takes on the values 0 or 1. And so I'm going to write it like this: phi to the y times 1 minus phi to the 1 minus y. Okay? And you saw this kind of notation when we talked about logistic regression. But all this means is that probability of y being equal to 1 is equal to phi, right? Because y is either 0 or 1. And so this is the way of writing probability of y equals 1 is equal to phi. Okay? And you saw a similar explanation notation when we're talking about logistic regression, right, 1 week ago, last Monday. And so the last parameter is phi. So this is Rn. This is also Rn. This is Rn by n. And that's just a real number between 0 and 1. Okay? So for any, let's see, so if you can fit mu0, mu1, sigma, and phi to your data, then these parameters will define P of x given y and P of y. And so if at test time you have a new patient walked into your office and you need to compute this, then you can compute, right, these things in the red and the orange boxes. Each of these is a number. And by plugging all these numbers in the formula, you get a number alpha P of y equals 1 given x, and you can then predict, malignant or benign tumor. Right? So let's talk about how to fit the parameters. So you have a training set. As usual, I'm going to write the training, let me write the training set like this. Xi, yi for I equals 1 through m. Right? This is the usual training set. And what we're going to do in order to fit these parameters is maximize the joint likelihood. And in particular, let me define the likelihood of the parameters. To be equal to the product from I equals 1 through m of P of xi, yi, parameterized by the parameters. Okay. And I'm just going to drop the parameters here, right, to simplify the notation a little bit. Okay. And the big difference between a generative learning algorithm like this compared to a discriminative learning algorithm is that the cost function you maximize is this joint likelihood, which is P of x comma y, whereas for a discriminative learning algorithm, we were maximizing this other thing, which is sometimes also called the conditional likelihood. Okay. So the big difference between these two cost functions is that for logistic regression or linear regression or generalized linear models, you were trying to choose parameters theta that maximize P of y given x. But for generative learning algorithms, we're going to try to choose parameters that maximize P of x and y, or P of x comma y, right? Okay. So, all right. So if you use maximum likelihood estimation, right? So you choose the parameters phi, mu 0, mu 1, and sigma that maximize the log likelihood, right? Where this you define as, log of the likelihood that we define out there. And so we actually asked you to do this as a problem set in the next homework. But so the way you maximize this is look at that formula for the likelihood, take logs, take derivatives of this thing, set the derivatives equal to 0, and then solve for the values of the parameters that maximize this whole thing. And I'll just tell you the answers you're supposed to get, but you still have to do the derivation. Right? The value of phi that maximizes this is, not that surprisingly. So phi is the estimate of probability of y being equal to 1. Right? So what's the chance when the next patient walks into your doctor's office that they have a malignant tumor? And so the maximum likelihood estimate for phi is just of all of your training examples, what's the fraction with label y equals 1? Right? So the maximum likelihood of the bias of a coin toss is just, count of the fraction of heads you got. Okay? So this is it. And one other way to write this is sum from I equals 1 through m, indicator let's see. So actually, we talked about indicator notation on Wednesday. Did you? No. Did you talk about indicator notation on Wednesday?
No.
Okay. Oh, so this notation is an indicator function where indicator yi equals 1 is returns 0 or 1 depending on whether the thing inside is true, right? So there's an indicator notation in which indicator of a true statement is equal to 1 and indicator of a false statement is equal to 0. So that's another way of writing this formula. Right? And then the maximum likelihood estimate for mu 0 is this. I'll just write out. And so, well, actually, if you put aside the math for now, what do you think is the maximum likelihood estimate of the mean of all of the features for the benign tumors, right? Well, what you do is you take all the benign tumors in your training set and just take their average. That seems like a very reasonable way. Just look at your training set, look at all of the benign tumors, all the O's, I guess, and then just take the mean of these, and that seems like a pretty reasonable way to estimate mu 0, right? Look at all of your negative examples and average their features. So this is a way of writing out that intuition. So the denominator is sum from I equals 1 through m, indicator yi equals 0. And so the denominator will count up the number of examples that have benign tumors, right? Because every time yi equals 0, you get an extra 1 in this sum. And And so the denominator ends up being the total number of benign tumors in your training set. Okay? And the numerator, sum prime equals 1 3m indicator is a benign tumor times xi. So the effect of that is whenever a tumor is benign, is 1 times the features. Whenever an example is malignant, is 0 times the features. And so the numerator is summing up all the features, all the feature vectors for all of the examples that are benign. Does that make sense? Okay, I'll just write this out. So this is sum of feature vectors for all the examples with y equals 0. Right, and the denominator is a number of examples with y equals 0. Okay? And then if you take this ratio, if you take this fraction, then you're summing up all of the feature vectors for the benign tumors, divide by the total number of benign tumors in the training set, and so that's just the mean of the feature vectors of all of the benign examples. Okay? And then right, maximum likelihood for mu1, no surprises, is sort of kind of what you'd expect. Sum up all of the positive examples and divide by the total number of positive examples and get their mean. So that's maximum likelihood for mu1. And then I'll just write this out. If you're familiar with covariance matrices, this formula might not surprise you, but if you're less familiar, then I guess you can see the details in the homework. Yeah, okay. Don't worry too much about that. You can unpack the details in the lecture notes or in the homeworks. Okay. But the covariance matrix basically tries to fit contours to that ellipse, right? Like we saw. So try to fit a Gaussian to both of these with these corresponding means, but you want one covariance matrix to both of these. Okay. So these are the so the way I motivated this was, I said, well, if you want to estimate the mean of a coin toss, just count the fraction of coin tosses, the came of heads, and then it seems like the mean for mu0 and mu1, you should just look at these examples and pick the mean, right? So that was the intuitive explanation for how you get these formulas. But the mathematically sound way to get these formulas is not via this intuitive argument that I just gave, is instead to look at the likelihood, take logs, get the log likelihood, take derivatives, set derivatives equal to 0, solve for all these values, and prove more formally that these are the actual values that maximize this thing, right, by setting derivatives 0 and solving. So you can see that for yourself in the problem sets. Okay? So, all right. Finally, having fit these parameters, if you want to make a prediction, right? So given a new patient, how do you make a prediction for whether their tumor is malignant or benign? So if you want to predict the most likely class label, you choose max over y of p of y given x, right? And by Bayes' rule, this is max over y of p of x given y, p of y divided by p of x, okay? Now, I want to introduce one more piece of notation, which is, I'm going to introduce, actually, how many of you are familiar with the argmax notation? Most of you, like, okay, two-thirds? Okay, cool. I'll go over this quickly. So let's just do an example. So the, let's see. So, you know, the min over z of z minus 5 squared is equal to 0, because the smallest possible value of z minus 5 squared is 0, right? And the argmin over z of z minus 5 squared is equal to 5, okay? So the min is the smallest possible value attained by the thing inside, and the argmin is the value you need to plug in to achieve that smallest possible value, right? So the prediction you actually want to make, if you want to output a value for y, you don't want to output a probability, right? You want to say, well, what do I think is the value of y? So you want to choose a value of y that maximizes this. And so there's the argmax of this, and this would be either 0 or 1, right? So that's equal to argmax of that. And you notice that this denominator is just a constant, right? It it's a p of x. Y doesn't even appear in there. It's just some positive number. And so this is equal to just argmax over y, p of x given y times p of y. Okay? So when implementing, when making predictions with Gaussian discriminant with generative learning algorithms, sometimes to save on computation, you don't bother to calculate the denominator if all you care about is to make a prediction. But if you actually need a probability, then you have to normalize the probability. Okay. So let's examine what the algorithm is doing. All right, so let's look at the same data set and compare and contrast what a discriminative learning algorithm versus a generative learning algorithm will do on this data set. Right. Here's an example with two features, x1 and x2, and positive and negative examples. So let's start with a discriminative learning algorithm. Let's say you initialize the parameters randomly. Typically, when you run logistic regression, I almost always initialize the parameters as 0, but it's just more interesting to start off for the purpose of visualization in a random line, I guess. And then if you run one iteration of gradient descent on the conditional likelihood, one iteration of logistic regression moves the line there. That's 2 iterations, 3 iterations, 4 iterations, and so on. And after about 20 iterations, it'll converge to that pretty decent discriminative boundary. Okay? So that's logistic regression, really searching for a line that separates positive and negative examples. How about the generative learning algorithm? What it does is the following, which is fit with Gaussian discriminant analysis. What we'll do is fit Gaussians to the positive and negative examples, right? And just one technical detail. I described this as if we look at the two classes separately because we use the same covariance matrix sigma for the positive and negative classes. We actually don't quite look at them totally separately, but we do fit two Gaussian densities to the positive and negative examples. And then what we do is for each point, try to decide what is this class label using Bayes' rule, using that formula. And it turns out that this implies the following decision boundary, right? So points to the upper right of this decision boundary, that straight line I just drew, you are closer to the negative class. You end up classifying them as negative examples, and points to the lower left of that line, you end up classifying as positive examples. And I've also drawn in green here the decision boundary for logistic regression. So these two algorithms actually come up with slightly different decision boundaries. Okay? But the way you arrive at these two decision boundaries are a little bit different. Okay. So, all right, let's go back to the. Any questions about this? Yeah. Oh, sure, yes, good question. So why do we use two separate means, mu0 and mu1, and a single covariance matrix sigma? It turns out that if you choose to build the model this way, the decision boundary ends up being linear. And so for a lot of problems, if you want a linear decision boundary, yeah, and it turns out you could choose to use two separate covariance matrix, sigma 0 and sigma 1, and that'll actually work okay, right? It's actually very reasonable to do so as well. But you double the number of parameters roughly, and you end up with a decision boundary that isn't linear anymore. But it's actually not an unreasonable algorithm to do that as well. Now, there's one Now, there's one very interesting property about Gaussian discriminant analysis. And it turns out that, well, let's compare GDA to a logistic regression. And for a fixed set of parameters, right? So let's say you've learned some set of parameters. I'm going to do an exercise where we're going to plot P of y equals 1 given x, parameterized by all these things, right, as a function of x. So I'm going to do this little exercise in a second. But what this means is, well, this formula, this is equal to P of x given y equals 1, which is parameterized by, right, well, the various parameters times P of y equals 1, which is parameterized by phi, divided by P of x, which depends on all the parameters, I guess. Right? So by Bayes' rule, this formula is equal to this little thing. And just as we saw earlier, I guess, right, once you have fixed all the parameters, that's just a number you compute by evaluating the Gaussian density. This is a Bernoulli probability. So actually, P of y equals 1 parameterized by phi, this is just equal to phi, is that second term. And you similarly calculate the denominator. But so for every value of x, you can compute this ratio and thus get a number for the chance of y being equal to 1 given x. Right? So I'm going to go through one example of what function you get for P of y equals 1 given x, for what function you get for this if you actually plot this for different values of x. Okay. So let's see. Let's say you have just one feature, x. So x is and let's say that you have a few negative examples there and a few positive examples there. Right. So it's a simple data set. Okay. And let's see what Gaussian discrete analysis will do on this data set. With just one feature, so that's why all the data is plotted on 1D. So let me map all this data to an x-axis. I just took this data and mapped it down. And if you fit a Gaussian to each of these two data sets, then you end up with, Gaussians as follows, where this bump on the left is P of x given y equals 0, and this bump on the right is P of x given y equals 1, right? And again, there's this technical detail that we set the same variance to the two Gaussians, but you kind of model the Gaussian densities of what does class 0 look like, what does class 1 look like with two Gaussian bumps like this. Oh, and then because the data set is split 50-50, P of y equals 1 is 0.5, right? So 1/2 prior, okay? Now, let's go through that exercise I described on the left of trying to plot P of y equals 1 given x for different values of x. So the vertical axis here is P of y equals 1 given different values of x. So let's pick a point far to the left here, right? With this model, if you actually calculate this ratio, you find that if you have a point here, it almost certainly came from this Gaussian on the left, right? If you have an unlabeled example here, you almost certainly came from the class 0 Gaussian, because the chance of this Gaussian generating example all the way to the left is almost 0, right? And so chance of P of y equals 1 given x is very small. So for a point like that, you end up with a point, very close to 0, right? Let's pick another point. All right, how about this point, the midpoint? Well, if you get an example right in the midpoint, you really have no idea. You really can't tell. Did this come from the negative or the positive Gaussian? Can't tell, right? So this is really 50-50. So I guess if this is 0.5, for that midpoint, you would have P of y equals 1 given x is 0.5. And then if you go to a point way to the right, if you get an example way here, then you'll be pretty sure this came from the positive examples. And so, you get a point like that, right? Now, it turns out that if you repeat this exercise, sweeping from left to right for many, many points on the x-axis, you find that for points far to the left, the chance of this coming from the y equals 1 class is very small. And as you approach this midpoint, it increases to 0.5 and then surpasses 0.5. And then beyond a certain point, it becomes very, very close to 1. Right? And we do this exercise and actually just for every point, for a dense grid on the x-axis, evaluate this formula, which will give you a number between 0 and 1, this is probability, and go ahead and plot, the values, you get a curve like this. And it turns out that if you connect up the dots, then this is exactly a sigmoid function. The shape of that turns out to be exactly a sigmoid function, and you prove this in the problem sets as well, right? Both logistic regression and Gaussian discriminant analysis actually end up using a sigmoid function to calculate, P of y equals 1 given x. Or the outcome ends up being a sigmoid function. I guess the mechanics is you actually use this calculation rather than compute a sigmoid function. But the specific choice of the parameters they end up choosing are quite different. And you saw when I was projecting the results on the display just now in PowerPoint that the two algorithms actually come up with two different decision boundaries. So let's discuss when a generative algorithm like GDA is superior and when a discriminative algorithm like logistic regression is superior. Let's see. Let me my board space into this. All right. So GDA, Gaussian discriminant analysis, so the generative approach, this assumes that x given y equals 0, this is Gaussian with mean mu 0 and covariance sigma. It assumes x given y equals 1, this is Gaussian with mean mu 1 and covariance sigma, and y is Bernoulli with parameters phi. Right? And what logistic regression does, this is a discriminative algorithm. Oh, this is some strange wind at the back, is it?
I see.
Okay, cool. All right. Yeah. Boy. No, there's just a scary UN report on global warming over the weekend. I hope we don't already have storms here. Okay, it's okay. Did you guys see the UN report? It's slightly scary, actually, the UN report on global warming, but hopefully, all right, good. Hurricane stopped. Okay. Let's see. So what logistic regression assumes is P of y equals 1 given x. That this is governed by a logistic function, right? So this is really, 1 over 1 plus e to negative theta transpose x. With some details about x0 equals 1, and so on, right? So just okay. So in other words, is assume that this is P of y equals 1 given x is logistic. Okay? And the argument that I just described just now, plotting P of y equals 1 given x point by point, really the sigmoid curve I drew on the other board, what that illustrates, it doesn't prove it, you prove it yourself in the homework problem, but what that illustrates is that this set of assumptions implies that P of y equals 1 given x is governed by a logistic function, right? But it turns out that the implication in the opposite direction is not true, right? So if you assume P of y equals 1 given x is governed by a logistic function, by this shape, this does not in any way, shape, or form assume that x given y is Gaussian, x given y equals 0 is Gaussian, x given y1 is Gaussian. Right? So what this means is that GDA, the generative learning algorithm in this case, this makes a stronger set of assumptions. And logistic regression makes a weaker set of assumptions because you could prove these assumptions from these assumptions. Okay? And by the way, let's see. And so what you see in a lot of learning algorithms is that if you make stronger modeling assumptions, and if your modeling assumptions are roughly correct, then your model will do better because you're telling more information to the algorithm. So if indeed x given y is Gaussian, then GDA will do better because you're telling the algorithm x given y is Gaussian, and so it can be more efficient. And so even if you have a very small data set, if these assumptions are roughly correct, then GDA will do better. And the problem with GDA is if these assumptions turn out to be wrong. So if x given y is not at all Gaussian, then this might be a very bad set of assumptions to make. You might be trying to fit a Gaussian density to data that is not at all Gaussian, and then GDA would do more poorly. Okay? So here's one fun fact. Here's another example. I'll get to your question in a second. Which is, let's say the following are true. Let's say that x given y equals 1 is Poisson with parameter lambda 1, and x given y equals 0 is Poisson with mean lambda 0, or lambda 1, lambda 0, and y, as before, is Bernoulli 5, right? It turns out that this set of assumptions also imply that P of y equals 1 given x is logistic, okay? And you can prove this. And this is actually true for any generalized linear model, actually, where the difference between these two distributions varies only according to the natural parameter of the generalized linear, of the exponential family distribution, right? And so what this means is that if you don't know if your data is Gaussian or Poisson, if you're using logistic regression, you don't need to worry about it. It'll work fine either way, right? So maybe you're fitting data to, maybe fitting a model, binary classification model to some data, and you don't know, is the data Gaussian, is it Poisson, is it some other exponential family model? Maybe you just don't know. But if you're fitting logistic regression, it'll do fine under all of those scenarios, right? But if your data was actually Poisson, but you assumed it was Gaussian, then your model might do quite poorly, okay? So the key high-level principles we want to take away from this is if you make weaker assumptions, as in logistic regression, then your algorithm will be more robust to modeling assumptions, such as accidentally assuming the data is Gaussian if it's not. But on the flip side, if you have a very small data set, then using a model that makes more assumptions will actually allow you to do better, because by making more assumptions, you're just telling the algorithm more truth about the world, which is, hey, algorithm, the world is Gaussian. And if it is Gaussian, then it will actually do better. Okay? There's a question in the back, or a few questions? Go ahead.
Just from a practical standpoint, do you know like what sort of data usually has the Gaussian property?
Oh, yeah, practical sample, what type of data is a Gaussian property? It's, yeah, it's a matter of degree, right? Most data on this universe is Gaussian, except for discrete data, I guess, yeah. So I think it's actually a matter of degree, right? If you plot, actually, if you take continuous value data, no, there are exceptions. You could plot it, and most data that you plot, will not really be Gaussian, but a lot of it you can convince yourself is vaguely Gaussian. So I think a lot of it is a matter of degree. I actually tell you the way I choose to use these two algorithms. So I think that the whole world has moved toward using bigger and bigger data sets, right? Digitalized society, which is a lot of data. And so for a lot of problems where you have a lot of data, I would probably use logistic regression, because with more data, you can overcome telling the algorithm less about the world. Right? So the algorithm has two sources of knowledge. One source of knowledge is what did you tell it, what are the assumptions you told it to make. And the second source of knowledge is learn from the data. And in this era of big data, we have a lot of data, there is a strong trend to use logistic regression, which makes less assumptions and just lets the algorithm figure out whatever it wants to figure out from the data. Right? Now, one practical reason why I still use algorithms like GDA, general discriminant analysis, or algorithms like this, is that it's actually quite computationally efficient. And so there's actually one use case at Landing AI that I'm working on where we just need to fit a ton of models and don't have the patience to run logistic regression over and over. And it turns out computing mean invariances of covariance matrices is very efficient. And so this is actually, apart from the assumptions type of benefit, which is a general philosophical point we'll see again later in this course, right? This idea about do you make strong or weak assumptions, this is a general principle in machine learning that we'll see again in other places. But as a very concrete, the other reason I tend to use GDA these days is less that I think it perform better from an accuracy point of view, but it's actually a very efficient algorithm. You just compute the mean covariance and then you're done, and there's no iterative process needed. So these days, when I use these models, it's more motivated by computation and less by performance. But this general principle is one that we'll come back to again later when we develop more sophisticated learning algorithms. Yeah.
If the data is generated from a Gaussian, but the covariance matrices are different, does the assumption that we just use the same covariance for performance make more?
Oh, right. So what happens if the covariance matrices are different? It turns out that it still ends up being a logistic function, but with a bunch of quadratic terms in the logistic function, so it's not a linear decision boundary anymore. You can end up with a decision boundary, that looks like this, right, with positive and negative examples separated by some other shape and a linear decision boundary. You could figure, actually, if you're curious, I encourage you to fire up Python NumPy and play around with parameters and plot this for yourself. Next question.
Is it recommended that we do some kind of statistical test to make sure that both distributions are Gaussian and have the same covariance before we do GDA?
Yeah, is it recommended that you do some statistical tests to see if it's Gaussian? I can tell you what's done in practice. I think in practice, if you have enough data to do a statistical test and gain conviction, you probably have enough data to just use logistic regression. I don't know. Well, no, that's not really fair. I don't know. If you're very high dimensional data, I think what often happens more is people just plot the data, and if it looks clearly non-Gaussian, then that would be a reason to not use GDA. But what happens often is that sometimes you just have a very small training set, and it's just a matter of judgment, right? Like if you have I don't know, 50 examples of healthcare records, then you just have to ask some doctors and ask, well, do you think the distribution is relatively Gaussian, and use domain knowledge like that, right? I think, by the way, another philosophical point, I think that the machine learning world has, frankly, a little bit overhyped big data, right? And yes, it's true that when you have more data, it's great. And I love data, and having more data pretty much never hurts. And usually, the more data, the better. So all that is true. And I think we did a good job telling people that high-level message. More data almost always helps. But I think a lot of the skill in machine learning these days is getting your algorithms to work even when you don't have 1 million examples, even when you don't have 100 million examples. So there are lots of machine learning applications where you just don't have 1 million examples. You have 100 examples. And it's then the skill in designing the learning algorithm matters much more. So if you take something like ImageNet, 1 million images, there are now dozens of teams, maybe hundreds of teams, I don't know. They can get great results if you have 1 million examples, right? And so the performance difference between teams, there are now dozens of teams that get great performance if you have 1 million examples for image classification like ImageNet. But if you have only 100 examples, then the high-skill teams will actually do much, 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 much better than the low-skill teams, whereas the performance gap is smaller when you have giant data sets, I think. So, and I think that is these types of intuitions, what assumptions to use, generative or discriminative, that actually distinguishes the high-skill teams and the less experienced teams and drives a lot of performance differences when you have small data. Oh, and if someone goes to you and says, oh, you only have 100 examples, you never do anything, then I don't know. If it's a competitor saying that, then I'll say, great, don't do it, because I can make it work. Well, I don't know. But I think there are a lot of applications where your skill at designing a machine learning system really makes a bigger difference when you have it makes a difference for big data and small data, but it just is very clear when you don't have much data, it's the assumptions you code into the algorithm, like is it Gaussian, is it Poisson, that skill allows you to drive much bigger performance than a lower skill team would be able to. All right, let's just, I just take questions from other people. Yeah, go ahead.
Does the implication mean just like, for example, if your primers come from like any member of the exponential, so not necessarily cosine?
Oh, sure. So does this, yeah, so what's the general statement of this? Yes, so if x given y equals 1 comes from an exponential family distribution, x given y equals 0 comes from an exponential family distribution, the same exponential family distribution, and if they vary only by the natural parameter of the exponential family distribution, then this will be logistic. Yeah. I think this was once a midterm homework problem to prove this, actually, but yeah. All right. Actually, let's take one last question and move on. Go ahead. Oh, does performance improvement hold even as you increase the number of classes? Yeah, I think so, yes. And the generalization of this would be the softmax regression, which I didn't talk about, but yes, I think a similar thing holds true for GDA for multiple. And so far, we only talked about binary classification. What if you have more than 2 classes? But yes, similar things holds true for like a GDA with 3 classes in softmax. Yeah. Oh yes, right. You saw softmax the other day. Right. Cool. And this theme that when you have less data, the algorithm needs to rely more on assumptions you code in. This is a recurring theme that we'll come back to as well. This is one of the important principles of machine learning, that when you have less data, your skill at coding in your knowledge matters much more. This is a theme we'll come back to when we talk about much more complicated learning algorithms as well. All right. So, I want a fresh board for this. So you've seen GDA in the context of continuous valued features X. The last thing I want to do today is talk about one more generative learning algorithm called naive Bayes. And I'm going to use as a motivating example email spam classification, but this I guess this is our first foray into natural language processing, right? But given a piece of text, like given a piece of email, can you classify this as spam or not spam? Or other examples, actually several years ago, eBay used to have a problem of, if someone's trying to sell something and you write a text description, right? Hey, I have a secondhand, Roomba, I'm trying to sell it on eBay. How do you take that text that someone wrote of a description and categorize it? Is it an electronics thing, or are they trying to sell a TV? Are they trying to sell clothing? But these are examples of text classification problems. So you have a piece of text and you want to classify it into one of two categories for spam or non-spam, or one of maybe thousands of categories if you're trying to take a product description and classify it into one of the classes. And so the first question we will have is, given an email problem, given an email classification problem, how do you represent it as a feature vector? And so in naive Bayes, what we're going to do is take your email, take a piece of email, and first map it to a feature vector x. And we'll do so as follows, which is first, let's start with the English dictionary and make a list of all the words in the English dictionary. Right? So first word in the English dictionary is a, second word in the English dictionary is aardvark, third word is aardwolf. That's easy, look it up. And then, email spam, a lot of people ask you to buy stuff, so the word buy, right? And then the last word in my dictionary is zigmergy, which is the technological chemistry that refers to the fermentation process in brewing. So again, this is a useful way to think about it. In practice, what you do is not actually look at the dictionary, but look at the top 10,000 words in your training set, right? But so maybe you have 10,000. It's easier to think about it as if it was a dictionary, but in practice, the other thing dictionary has too many words, but the other way to do it is to look through your own email corpus and just find the top 10,000 occurring words and use that as a feature set. And so, I don't know. Right, in your emails, I guess you're getting a bunch of email from us or maybe others about CS229. So CS229 might appear in your dictionary of building an email spam filter for yourself, even if it doesn't appear in the official, was it like the Oxford dictionary? Just yet, just you wait. We'll get CS229 there someday. All right, and so given an email, what we would like to do is then take this piece of text and represent it as feature vector. And so one way to do this is you can create a binary feature vector that puts a 1 if a word appears in an email and puts a 0 if it doesn't. Right? So if you get an email that asks you to buy some stuff, and if the word A appears in the email, you put a 1 there. They're not trying to sell aardvark or aardwolf, so 0 there. Buy, and so on. Right? So you take an email and turn it into a binary feature vector. And so here, the feature vector is 0, 1 to the n, because it's an n-dimensional binary feature vector, where for the purpose of illustration, let's say n is 10,000, because you're using, take the top 10,000 words that appear in your email training set as the dictionary that you will use. So, so in other words, xi is indicator word I appears in the email, right? So it's either 0 or 1, depending on whether or not that word I from this list appears in your email. Now, in the naive Bayes algorithm, we're going to build a generative learning algorithm. And so we want to model P of x given y, right, as well as P of y. Okay? But there are 2 to the 10,000 possible values of x, right? Because x is a binary vector of this 10,000 dimensional. So we try to model P of x in the straightforward way as a multinomial distribution over 2 to the 10,000 possible outcomes, then you need, right, 2 to the 10,000 parameters, right, which is a lot. Or actually, technically, you need 2 to the 10,000 minus 1 parameters, because they add up to 1, so you save 1 parameter. But so modeling this without additional assumptions won't work, right, because it's excessive number of parameters. So in the naive Bayes algorithm, we're going to assume that the xi's are conditionally independent given y. Okay? Let me just write out what this means. But so p of x1 up to x 10,000 given y, by the chain rule of probability, this is equal to p of x1 given y times p of x2 given x1 and y times p of x3 given x1, x2, y up to p of x 10,000 given and so on, right? So I haven't made any assumptions yet. This is just a true statement of fact. It's always true by the chain rule of probability. And what we're going to assume, which is what this assumption is that this is equal to this first term, no change, but x2 given y, p of x3 given y times dot 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 p of x 10,000 given y. Okay, so this assumption is called a conditional independence assumption. It's also sometimes called the naive Bayes assumption, but you're assuming that so long as you know y, the chance of seeing the word advok in your email does not depend on whether the word a appears in your email, right? And this is one of those assumptions. It's definitely not a true assumption in that this is just not a mathematically true assumption. Just that sometimes your data isn't perfectly Gaussian, but if you assume it's Gaussian, you can kind of get away with it. So this assumption is not true in a mathematical sense, but it may be not so horrible that you can't get away with it, right? And so side aside, if any of you are familiar with probabilistic graphical models, if you've taken CS228, this assumption is summarized in this picture. And if you haven't taken CS228, this picture won't make sense, but don't worry about it. Right, that once you know the class label, is it spam or not spam, whether or not each word appears or does not appear is independent. Okay, so this is called conditional. So the mechanics of this assumption is really just captured by this equation. And you just use this equation, that's all you need to derive naive Bayes. But the intuition is that if I tell you whether if I tell you that this piece of email is spam, then whether the word buy appears in it doesn't affect your beliefs about whether the word mortgage or discount or whatever spammy words appear, right? So just to summarize, this is product from I equals 1 through n of p of xi given y. All right. So the parameters of this model are, I'm going to write phi subscript j given y equals 1 as the probability that xj equals 1 given y equals 1, phi subscript j given y equals 0, and then phi. Right. And just to distinguish all these phi's from each other, I'm going to just call this phi subscript y. Okay? So this parameter says if it's spam email, if y equals 1 is spam, y00 is non-spam. If it's spam email, what's the chance of word J appearing in the email? If it's not spam email, what's the chance of word J appearing in the email? And then also, what's the class prior? What's the prior probability that the next email you receive in your inbox is spam email? And so, to fit the parameters of this model, you would, similar to Gaussian discriminant analysis, write out the joint likelihood. So the joint likelihood of these parameters, right, is the product, given these parameters. Right, similar to what we had for Gaussian discriminant analysis. And the maximum likelihood estimates, if you take this, take logs, take derivatives, set derivatives to 0, solve for the values that maximize this, you find that the maximum likelihood estimates of the parameters are phi y is pretty much what you'd expect. Right, it's just a fraction of spam emails. And phi of j given y equals 1 is, well, I'll write this out in indicator function notation. Oh, shoot, sorry. So that's the indicator function notation of writing out, look through your training set, find all the spam emails, and of all the spam emails, i.e. examples of y equals 1, count up what fraction of them had word J in it. Right? So your estimate of the chance of word J appearing, your estimate of the chance of the word by appearing in spam email is just, well, of all the spam emails in your training set, what fraction of them contained the word by? What fraction of them had xj equals 1 for, say, the word by, okay? And so it turns out that if you implement this algorithm, it will nearly work, I guess. But this is naive Bayes for email spam classification, right? And I'll mention the one reason this, and it turns out that with one fix to this algorithm, which we'll talk about on Wednesday, this is actually a not too horrible spam classifier. Right? It turns out that if you use logistic regression for spam classification, you do better than this almost all the time. But this is a very efficient algorithm because estimating these parameters is just counting, and then computing probabilities is just multiplying a bunch of numbers. So there's nothing iterative about this. So you can fit this model very efficiently and also keep on updating this model even as you get new data, even as you get new users mark as spam or whatever. Even as you get new data, you can update this model very efficiently. But it turns out that actually the biggest problem with this algorithm is what happens if this is 0 over if you get zeros in some of these equations, right? But we'll come back to that when we talk about Laplace smoothing on Wednesday. Okay. All right. Any quick questions before we wrap up? No? Okay, good. So now you learn about generative learning algorithms. We'll come back on Wednesday and learn about some more fine details of how to make this work even better. So let's break. We'll see you on Wednesday.